And then all problems will be similar to homework. Some of them will not be on a practice set, but most of them probably. You can probably pass by doing the practice test and making sure you do all problems similar to that. If you want to get an A, you need to be able to do all problems similar to homework to be able to do those. All right. Thursday of next week, we'll have a review for this test. So make sure you come or watch online then. All right, well, today I just wanted to do a couple of review problems on solving triangles. And I just wanted to remind you that we said for applied problems, we want to make a sketch. And we want to sketch all the given quantities and the desired ones we want to put a variable in. All right. Then also label or compute and give any obvious consequences. Like if you got supplementary angles, go ahead and compute the supplementary angle. Anything easy. If you got two sides of a right triangle, maybe you do the third one by the Pythagorean theorem if you think you might need it. Okay, also compute any obvious consequences. And this will really help you figure out some of these. Here's a nice problem in the set that we didn't look at last time. Suppose we want to consider a building that has a lightning rod on top. And you're curious, how tall is that lightning rod? And then we'll say, if you were to measure your position from 500 feet, I think it is. Let's see. Yeah, 500 feet away from the base of the building. You measure 36 degrees to the top of the building. And 38 degrees to the top of the lightning rod. How tall is the rod, right? On all these problems, unless we say otherwise, we will assume, right, that the ground is horizontal and the building is vertical. So here's the situation, the sketch. I can make a building. And then I can put a lightning rod on the top. And you stand 500 feet away along horizontal ground, so this is a right angle. So here's the building. And you label that 500 feet. Then you measure up here, and you say that's 36 degrees. You measure up here, and that's 38 degrees. Once you draw this, this is a whole lot, makes a whole lot of sense because now you see some right triangles in here, right? What do I do with that? Well, I haven't labeled one thing. I labeled all my given numbers, but I didn't label what I'm trying to find. So let's call this H. How can I find H is the idea. The trick, oh, I forgot to write on here also. Recognize that you can solve any right triangle given any two sides or a side and an angle. Two independent pieces of information, not two angles, because that's just one piece of information, right? They're complementary. Once you know one, you know the other. You can solve any right triangle given two sides or a side and an angle, two independent pieces of information. So I look at this one and immediately say, oh, look, 36 degrees and 500 in this right triangle. I can solve it. I can find anything I want out of there. 38 degrees on this side of this triangle. I can solve that one. So I solved both triangles, and now I recognize maybe I should label this with some letter. I don't know what it is yet, X. And I just use the big triangle to find this length, the little triangle to find this length, and I can subtract them to find the height of the tower. So there's where the picture shines. You can see what to do. So by trigonometry, right, I'll say I want to relate in a small triangle two things I know and one thing I don't know. So I can solve for the thing I don't know. And what I'm interested in really is X. So I want to find X knowing this side and this angle. So I say, well, what relates this angle, the opposite side and the adjacent side, either sine or cosecant. Cosecant's not on my calculator, so I'll use sine. And I'll say sine 36 degrees in the small right triangle. Oops, not sine, I'm sorry, it's tangent. Opposite over adjacent tangent of 36 degrees is x over 500. And then similarly, I can use tangent on this one because I want to find this side length given this angle and this one. That's opposite over adjacent also. So tangent 38 degrees is equal to opposite side x plus h over the adjacent side 500. So I can take these two equations and write equivalently in the first one by multiplying by 500, that x equals 500 times tangent 36 degrees. This is why you need a calculator in the first test. I should have written that down there. You need to bring a calculator for that. Also, if you're online and can't come in, I understand that, send me some sort of note to that effect, or you can arrange it with the testing center if you want. The Student Disability Services, if you have qualifications, and you can take the test with them, or you can work out something with me if you can't come in. All right, so I'm going to take 500 tangent 36, and I get to the nearest foot 363. Then this one I'll multiply through by 500, and I get x plus h is equal to 500 tangent 38. This one comes out be 391 feet. And now we can just subtract them, right? We can say h is equal to x plus h, the latter number, less x. I'm just looking at the picture here, or we're looking at these. It comes out to be 391 minus 363. This must be a 28-foot tall lightning rod. I'd like you to be able to do that kind of problem. You can get multiple triangles and figure out various things in there. Let's just leave it there then. Are there any other homework problems you want to look at? Did you look at some of these others? Have any troubles or interest in looking at anything else?
2C.
Which one?
2C.
2C, okay. So to finish up this section on solving triangles, which I told you is extremely important. This will be on the exams, including the final. Here's a review problem. Find the length of the missing sides is out of 5.4, the UCO supplement. In other words, solve, find the side, it just says. If you're given that sine B equals 1 over square root 3, and A is equal to 2. So on these, it really helps to draw the triangle. And here, this B is what I would call theta. It means the angle opposite side B. So if I put A over here equal to 2, then B has to be the other leg. And C is the hypotenuse. And I'll put theta, or B here, capital B, opposite side little b. Now, once I draw the triangle, I can say, well, I have A, I just need C and B and C. And I have, instead of the angle, I have the sine of the angle. So what I do is I say, well, sine 1 over square root 3 is sine B. But sine B, or beta, has to be its opposite side over the hypotenuse. It has to be B over C. Oh, so this one's trickier than, yeah. Okay. All right, so then from this one, we can say, this implies by multiplying through that C times 1 over square root 3 is equal to B. That's the best way to do this. And then we can use, let's say, the Pythagorean theorem and say C is the square root of B squared plus A squared. All right, Pythagorean theorem. And get that equals B. But now A is 2, all right? So now I'm going to write that in here. Yeah, we didn't do one like this last time, did we? So it says square root of 2 squared plus B squared over square root 3 equals B by putting in A. And now, if I square both sides, the square of the left is 2 squared plus B squared over 3, which is called 2 squared 4. Right? And the right side is B squared. So they're squaring both sides. And now we can solve this, right? Because we just got it down to one variable. 4/3 plus 1/3 B squared equals B squared. If I subtract 1/3 B squared from each side, then I get 4/3 equals 2/3 B squared. And then multiply both sides by 3/2 gives us 1/2 equals B squared. Tells me that by square rooting B must be 1 over square root 2. Which you can write that way, or you can rationalize and call it square root 2 over 2. This is where the picture really helps. You know, you look at this and say, well, wait a minute, there's Pythagorean theorem because it's a right triangle. I know this one, I can figure this out. Yeah, good one. Any others you want to look at? There is another way to do this. I did this without any computation, so I found it exactly. Did the answer in the back put that square root or just give it decimal?
It was actually just square root of 2. C was square root of 6.
Give you what?
The B was square root of 2 modifier.
Instead of 1 over square root 2?
Yeah.
I got a different answer. I hope our answer key isn't wrong. Let's see if I did this wrong myself, huh? So I wrote this down. Sine B is 1/√3. And A is 2. So sine B over C, 1/√3, that's correct. Multiply by C, you get C/√3 equals B. But C is equal to, since it's the hypotenuse, is square root A squared plus B squared. Square both sides. So I'll bring this up here and put 2 for A. Square both sides. Four thirds plus 1/3 B squared equals B squared. 4/3 equals. Oh, I did this step wrong. That's what I did. It's my mistake, right? I multiplied by 3/2 on both sides. I got the wrong result. This should have been 2 equals B squared. This is why you should check your answers again, right? Multiply both sides by 3/2 and get 2 equals B squared, and then so B equals square root of 2. Thank you. Okay, so if they write that, that's what they want you to, we want you to do. I hope to write some of these. I have the following comment. In the field, you can also do another thing. For approximate answers, you can also say sine B equals 1/√3 tells me that B is inverse sine of 1/√3. As long as it's in a triangle, I can calculate that way. Now I can run that on my calculator. So let's see. Inverse sine 1 divided by square root 3 gives me 35.264, etc. All right. And once I have B, then I can say, well, I know B or beta and this side, and if I want to find, oh, I didn't finish here either. I just found B, then I'm supposed to find C, right? I should have put down here, once you find B, then C is the square root A squared plus B squared. A was 2, B was square root 2. That's what you were saying there at the end. 2 squared plus square root 2 squared is square root 6. There we go. So there's the other two sides. B is square root 2 and C is square root 6 by the Pythagorean theorem to finish that. All right. But you can compute it this way, and then you can calculate the other sides from this angle approximately. You can say A, we've got A, B, B over A is tangent angle capital B. And we've got A equals 2. We got B over 2 equals tangent 35.264, etc. degrees. Gives you B equals twice that tangent. So if I take 2 times tangent I have here, I get 1.414, which maybe I can recognize as square root 2, not in general, but don't memorize all the square roots, but you do get the answer to however many decimal places you carried that. And then you can calculate C as a decimal. It's square root A squared plus B squared, 2 squared plus 1.414 squared. And you should get 2.449. So if you want an exact answer, then you can use the Pythagorean theorem here. If you want an inexact answer, it's probably easier to calculate b equals arc sine. So I would like you to do this and get the same kind of answer it has on the back. You'll be able to do this exactly, but here's how you can approximate it. Okay. Any others? I just put this one up because it's easier. And if you don't have some special perfect number like 1 over square root of 3, just have a decimal approximation, then this is just as good. All right, well, today we're going to do graphs of sine and cosine. How about that? How do you graph things like y equals x squared in algebra? Remember that? You just usually plot points in from a table and try and sketch a smooth curve through them. That's what we're going to do here. So we make a table of the special angles. And then we can use those to see what the graph looks like. Suppose I put theta versus y equals sine theta, right? What do I get? If I put theta equals 0, what do I get? I can run to the unit circle and do it there because remember we said all these trig functions are defined by the unit circle. So you start out by putting a terminal ray, excuse me, equals 0, right? And you go 1 unit out on the circle to the point 1, 0. So you infer then that this is the cosine of 0 and the sine of 0, respectively, right? This is cosine 0, sine 0, since we went at 0 degrees, radians. We're going to do this plot in radians. That's what's useful in most applications, right? So we'll say, oh, the sine of 0 must be 0, and put that in. Now we go and turn this 30 degrees, take 1/3 of a right angle here, and we call that pi over 6 radians. And if we drop a perpendicular here, we observe it's a 30, 60, 90 triangle, right? 1/2 square root 3 over 2, and 1 since it's a unit circle. Now this point has coordinates square root 3 over 2, 1/2. So that's the cosine and sine of pi over 6. In other words, I put in pi over 6, and the y coordinate is 1/2. Pi over 6. There we go. And then the next special angle I know of is pi over 4, right? At pi over 4, I come out here, and remember, you drop the perpendicular, you get the 45, 45, 90 triangle. So the coordinates here is square root 2 over 2, square root 2 over 2. The y coordinate is square root 2 over 2. It follows that pi over 4, that angle has sine square root 2 over 2. So I'm just making a table. Here's another one. If I do it at pi over 3, right, a 60-degree angle, then this thing has to have coordinates, right? Square root 3 over 2.5. The y coordinate being 1/2, I say that's the sine of pi over 3. And then at pi over 2, it's an easy one, right? I turn to pi over 2. I have this angle. It goes through the point 0, 1. So I infer that the sine of 90 degrees or pi over 2 radians is the y coordinate 1. There I have all the special angles up through pi over 2, at the right angle. So let's continue. Suppose I put special angles past here. What 3 angles come in here? Well, this angle right here is pi over 3, right? If you think about it. 1/3 of the way through here. If this is 30 degrees past 90, so it's 120 degrees, you can multiply it by pi over 180 and find out this is pi over 3, or you can say it's pi over 6 past here. Gives you that. So the next special angle is pi over 3. And I observe that for this 30, 60, 90 triangle, I have square root 3 over 2 here and 1/2 here. The y coordinate is plus square root 3 over 2 again. Just, oops. This was square root 3/2. I didn't write it correctly. It's square root 3/2 again. And then I go to this angle here, 135 degrees, the next special angle. I drop the perpendicular, I got 45, 45, 90 triangle. This is also known, coming to here, as 3 pi over 4. So we'll go to 3 pi over 4 and say now we get square root 2/2. This is the height, the y coordinate. This is square root 2/2, square root 2/2. And this one here is minus square root 2/2 because I went left, and then square root 2/2. I want the coordinates, not just the side lengths. This one here was a half to the left, so I get minus a half. Square root 3/2 up gives me plus square root 3/2. And now the y coordinate is square root 3/2. But I'm at this angle here, which is 5 pi over 6. Finally, if I get to pi radians, this angle here, pi, this takes me back to the point minus 1, 0, and the y coordinate sign is again 0. Now what happens if I start doing larger special angles, right? Suppose I go, for instance, here to 7 pi over 6, right? I'll go pi plus pi over 6, another 30 degrees. I drop the perpendicular. The perpendicular here. And it comes to the same point as here. So I've got actually minus the y coordinate at 7 pi over 6 as I had at 5 pi over 6. And so you can keep going. 7 pi over 6 just gives minus this coordinate, minus square root 3/2. If I go to 5 pi over 4, right, 45-degree angle into this quadrant. Now I drop a perpendicular, land same place as this one, at the same place as 3 pi over 4, except negative y. All right, and so I get minus square root 2/2, and I notice I'm just running these numbers backwards all the way back here, and so I'd say et cetera, et cetera, et cetera. There's an important point here at 3 pi over 2, right here. I come down to 0 minus 1. See if I can squeeze this in. 3 pi over 2. The y coordinate is minus 1. That's important because that's the smallest y coordinate, right? Is at the bottom of the unit circle, 1 unit down. So at 3 pi over 2, the y coordinate is minus 1. I plot that. And then at the last important point at 2 pi, right, all the way around, I get back to where I started. The sign is again 0. And then what's going to happen if I keep going around and around? I'm going to repeat those y values, right? Because all coterminal angles have the same sine and cosine. So if I go around here to 2 pi plus pi over 6, I'm going to get a half again. 2 pi plus pi over 4, I'm going to get square root 2/2 again. So this is now going to repeat every 2 pi units because 2 pi is a whole rotation. Say repeat. There it is. I built up a wonderful table, and I brought this diagram this morning for you. Video online from Math is Fun here. Let's see if I can camera over here. Oh, I've got people waiting to come in. I didn't see. Sorry, I didn't see you waiting online. I'll try and let you in, but sometimes I don't see. We've been doing graphs of sine and cosine here. So we're doing y equals sine theta. I built up this big table from the unit circle if you just came in. I'll move this over and show what's happening. The idea is that the sine of the angle is the y coordinate. So what this is plotting is that if you're some angle here, then the y coordinate plots here, and this is moving along the x-axis. You're plotting the theta axis. You're plotting for each theta the height y on the unit circle. That's what we're going to wind up plotting here. Kind of a neat illustration, I think. In other words, if I plot this table I just built up from the unit circle, I get this graph. There's theta, which is y, and I plot y equals sine theta. I notice that the largest y coordinate in here is 1, and the smallest y coordinate is minus 1. So I only need to plot between plus 1 and minus 1, and I'll put these guidelines on here. You don't have to, but it's kind of convenient, it turns out. And I'm gonna go up and down between those. I'm gonna start at the point 0, 0, because if I put angle 0, the sine of the circle here was the y coordinate 0. And then when theta was pi over 6, I had this little triangle here, and I got y was a half. So at pi over 6, I'm going to come halfway up here to the half and plot that point. At pi over 4, right, we got square root of 2 over 2, so that's going to be a little higher. And at pi over 3, I got up to this point here, square root of 3 over 2 was the sine, just using all the special triangles. And then at pi over 2, sine was equal to 1, so I plot this point on the guideline 1. And what happens, you can get your calculator and fill these in between, you get a nice smooth curve. This is a lot like plotting y equals x squared in algebra, right? You just plot a bunch of points, put a smooth curve through them. There it is. There's the first part of the graph of sine. Now what you notice is it comes down to the same way, right? This went back to square root 3 over 2, so does this. Then square root 2 over 2, 1. This should have been 1/2. Golly, 1/2, 1/2, and 0. So this was a half here. And so this is going to come down with the same set of points. Square root 3 over 2, square root 2 over 2, 1/2, and then 0. And this will be pi. This is 5 pi over 6, 3 pi over 4, 2 pi over 3. So plotting all these special triangles, you find out that it does this. And then what happened after it reached pi? We said each time you hit a special angle, you get the negatives of these. So spaced correctly. And then until you get back to 2 pi, where you get at 2 pi, you get what theta equals 0, or y equals 0. And so it goes down the same way it went up. And it has a minimum here at 3 pi over 2 of -1. But you plot the same y coordinates, minus a half, except negative, minus a half, minus square root 2 over 2, minus square root 3 over 2, and they come down like this. And there's your graph of sine. Now they start repeating. What does that mean? That means you can keep drawing this wave. It's the wave that never ends, as they call it, right? A real wave, a sine wave, is a repeating pattern like this. The reason it repeats, right, is that once you go around here, after 2 pi, you go another pi over 6, you get a half, you get another pi over 4, you get square root 2 over 2, and so on. You get the same values. The wave looks the same. And you can let theta be negative, right? And it will also repeat because once again, it's periodic. So here is our graph of y equals sine theta. Looks just like that. And I'll put it up over here. Here's a computer generated graph. Always looks a little better. There's this yellow curve here. That goes up to 1, crosses at pi, goes back down to -1 of 3 pi over 2, goes back to 0. So you notice that interesting things about this symmetrically. It repeats every 2 pi units. So if this is 2 pi, this is 2 pi, and this is 2 pi, it keeps repeating this, what we call one period here. One period is where it goes all the way to the top, all the way to the bottom, and comes back to where it starts. One period at 2 pi units repeats over and over, both directions. That's a wave, something that repeats forever. Not just a pulse that is a single bump going down. And then it has this symmetry that it's 0 at 0 and 2 pi, and it's 0 halfway in between. And halfway in between those, it's at the top. Halfway between these here, it's at the bottom. Goes between plus and -1. Now, what about the cosine? Similarly, plotting the x coordinates off of that, we'll get the cosine, and this is what we get. And it looks the same shape, doesn't it? Well, with good reason, because the x coordinates are just repeating. If you look at the x coordinates I drew on the unit circle, they're repeating the same numbers, just a little bit off because they have this additional identity that we can consider now. And actually, it's in chapter 5, but we just didn't cover it till here where we're going to use it. How do you plot cosine? One way is we can plot the x coordinates. Similarly, get the graph of y equals cosine theta. And since the x coordinates are actually all the same, but just starting with x equals 1, the cosine starts when theta equals 0, x equals 1 here. It starts at the top of its period, right? When you take a 0 angle, the x coordinate is 1, and then the x coordinate goes down to square root of 3 over 2, down to square root of 2 over 2. I wrote this backwards. That's what I did. This should have been 1/2 square root of 3 over 2. That's why I wrote it wrong in there. 1/2 square root of 3 over 2. X and y. So x is 1/2, and then x is 0. So the cosine is going to look like this. While this one's coming up, this one's going to go down in exactly the same way. And it hits pi over 2 here. When it gets down to pi, you know, when the angle gets to pi, the cosine, the x coordinate is -1, right? Let me get the circle. And then at 3 pi over 2, when you go around this angle, the x coordinate is 0, so cosine is 0, and so you plot this one. And then all the way around to a whole rotation at theta equals 2 pi, the x coordinate is back to 1. So it actually looks exactly the same shape. There it is, y equals cosine theta. All right. And it repeats forever and ever also. And one more thing, we can say this is exactly the same shape. It looks like it from the table, but in fact, it is exactly the same shape. And here's the reason. It's just shifted pi over 2 units left, pi over 2 radians left. That's what this graph is, right? Pi over 2 apart, they do the same thing. They're both 1 here, and then pi over 2 more, they're both, oops, pi over 2 later, they're both 0, and then pi over 2 later, they're both -1. So they, but here's why. We can prove this by the so-called cofunction identity. And I'll only prove the cofunction identity for acute angles, but it holds for all angles, so it holds in that. The cofunction identity looks like this. I like this proof just because it's simple, even though it doesn't prove it for the unit circle for all those angles, right? But we'll say, suppose we put any angle theta in a right triangle. You can extend this to unit circle and make it a proof for all angles. Then what is this angle here? This has to be 90 degrees minus theta, right? Or in radians, pi over 2 minus theta. Same thing, right? Now let's call this side A, call this side B, and this side C. We observe from the triangle that the sine of theta is A over C, opposite over hypotenuse, right? What's the cosine of this angle? Cosine of 90 minus theta is its adjacent side, the side adjacent to this angle, divided by the hypotenuse. So the sine of theta is equal to the cosine of this complementary angle, pi over 2 minus theta. See that other triangle? Right? Sine of this angle is this opposite over. This cosine of this angle is its adjacent side of the hypotenuse. It's all A over C in either case. Same thing the other way. If cosine of theta, what's that? Well, it's adjacent over hypotenuse B over C, but that's the opposite over the hypotenuse for this angle. These are called cofunctions identities. Now this is the proof. Let's scratch out the middle, and this is called a cofunction identity. Sine of any angle is equal to the cosine of its complementary angle, 90 degrees minus that angle, right? And the cosine of an angle is equal to the sine of 90 degrees minus that one. So you put pi over 2 or 90 degrees, it doesn't matter. But that's the cofunction identities for sine and cosine. They're cofunctions, sine and cosine, both of them. The cofunction is of the complementary angle is the same as the function of the original angle. And it holds for the other angles in pairs also. Tangent theta, what's that? Opposite over adjacent is A over B, but that is, for this one, opposite, I'm sorry, adjacent over opposite, the cotangent of the other angle, pi over 2 minus theta. And then similar to the cotangent of theta, cotangent is adjacent over this one is B over A. That's the opposite over the adjacent for the complementary angle. The tangent. And so tangent and cotangent come in pairs also, hence the name cofunction identity. The tangent of any angle is the cotangent of its complementary angle. The cotangent is the tangent of the complementary angle. And finally, secant and cosecant are the same way. We'll just say secant theta is cosecant, similarly, of pi over 2 minus theta. And secant, cosecant of pi of theta is the secant of pi over 2 minus theta. So there's 6 cofunction identities, each function and its cofunction, secant and cosecant, tangent and cotangent, sine and cosine, all have this nice relationship. Now, the reason I put this up now is we can use it to prove that actually these things are the same graph shifted pi over 2 from each other. That's what they look like. By the first of these, we observe that sine theta and each of the angles is cosine of pi over 2 minus theta, right? That's the cofunction identity. And now we also know that cosine is an even function. Remember what even means? Cosine, the cosine of a negative angle is the same as the cosine of a positive angle, right? A function is even if f of minus x is equal to f of plus x. So we use the even identity. Since cosine is even, cosine of minus alpha an angle is equal to cosine of plus alpha, right? Cosine is even like this. That's the even identity. And so if I call this alpha, cosine of pi over 2 minus theta is the same as the cosine of theta minus pi over 2 minus this angle. But what's this? This is the cosine function shifted by pi over 2, right? You have to make theta pi over 2 greater to get the same cosine value. So this is the cosine theta shifted pi over 2 units. So that says you can shift the cosine pi over 2 units to sketch the sine. Here's cosine, 0 to 2 pi. It repeats a wave every 2 pi units, going between 1 minus 1. Here's the guidelines. Now, how do I sketch the sine from that? I just graph the whole thing. I sketch take the cosine and move it over pi over 2 units to get sine. So this was pi over 2. I just start the sine here and I do the same thing. And then also this one comes down here. So you just shift every point by pi over 2 units, right? This one gets shifted over pi over 2 units. And this one gets shifted over pi over 2 units. I have to draw the cosine in green, shouldn't I, just to break them up. Here's cosine. And then the white one, by shifting over pi over 2 units, gives me the sine. How about that? So the cofunction identity proves that they're actually the same shape, just shifted over by 90 degrees or pi over 2 units. For this reason, we call both of these as sine waves. They're waves because they repeat a pattern over and over. Since the sine function is a wave, we call it a sine wave. And since the cosine function is the same shape, we'll just call it a sine wave too. Right? You notice I've done, oh, I should call this y equals cosine theta still. I made the graph of theta here, right? So this is theta versus y still. All right, so those are the graphs of sine and cosine. Very, very useful because in industry and engineering and physics and lots of other applied sciences, whenever you do vibration analysis or radiation analysis, they always look at breaking it down into the sum of these kind of waves. You know, if they measure your voice on one of those oscilloscopes, they'll say, what's the strength? They'll write it as a sum of these kind of waves, and we'll say, what's the frequency of the different waves? So these are actually extremely useful in vibration analysis. One thing else I wanted to do here too, let me put this up real quick. This is a chart that, where'd this go? In the process of doing this, we came up with a really useful tool. A lot of people, when they start to see all these same points have the same coordinates, just like here, this one is the same as this one, just with a minus on the x coordinate. This is the same as this one, a minus on the x coordinate. These have minus on both the x and y coordinates of these, right? These have minus the y coordinate of these and plus the x coordinates. They just memorize this circle for all the important special angles, right? 30 degrees, 45, 60, 90, all multiples of 30 and 45. This shows all the special angles within one rotation. And by looking at the coordinates, you can immediately tell the sine and cosine. Like somebody says, what's the sine of 135 degrees? If I memorize this circle, I just go to 135 degrees and I recognize this point is minus square root 2 over 2, square root 2 over 2. So the cosine is minus square root 2 over 2 and the sine is plus square root 2 over 2. Some people like to memorize this or hand it out in classes. I don't like to hand it out in classes because I want you to figure it out. Personally, I like to just imagine the 135 degrees in my mind and remember that if I drop this, it's a 45, 45, 90 triangle, and so I get these coordinates. But I do want to point out that a lot of people find this very useful for memorizing all these different points, and then you can figure out the sine and cosine of any special angle up to 360 degrees. And so most of these show also the radians measure, pi over 6, pi over 4, and so forth. This one just shows the degrees. Okay, so there's the point. The first coordinate's always the cosine, the second one's the sine. This unit circle is a really useful tool that some people may want to. Okay, so there's a graph of sine and cosine, but in practice in engineering and so forth, you're not so interested in a wave that's 1 unit tall, right? Maybe, you know, your current in your circuit will oscillate like this. You'll have a sine wave for the oscillatory current. There's a good reason for that, actually. Often you get that, but it might be stronger. Maybe it's not, the current isn't 1 amp, it's 10 amps. So you need to make this 10 times as tall. Or maybe it oscillates faster. It doesn't oscillate every 2 pi seconds. It oscillates every second. You know, so you have a frequency of different than that. How can you stretch this thing vertically and horizontally? We use this from algebra techniques. We can now sketch more exotic curves that are waves. We can more generally, and we'll expand this a little further next time. Maybe we'll get to it today, I don't know. We can more generally sketch the graphs of y equals a sine bx, where a and b are numbers, or y equals a cosine bx. And these are just, I'm going to claim, stretches and flips of the basic 2 graphs that we showed right there. How can we do that? Recall from algebra that given y equals f of x, how do we sketch y equals a f of x? If we multiply the function on the outside by a number a, what does that do? It multiplies every y coordinate by a, so this is absolute value of a times its tall. Let's say it's stretched or shrunk. If a is a half, then it's half as tall. If a is 2, then it's twice as tall, right? So it's stretched by absolute value of a. And then if a is negative, it makes all the y coordinates negative also. So it's flipped vertically over the x-axis if a is negative, because it makes the y coordinates negative instead of positive. Now, what does the b do? Similarly, if I took just y equals a, I'm sorry, not a, f of bx, now what happens? This one, x has to be 1 over b times the number, times what it used to be to get the same number in here and get the same y value out. So actually now this is stretched or shrunk. I say stretched, but it means stretched or shrunk by a factor of 1 over absolute value of b, because x has to be b times as big to get the same number, and flipped horizontally since it makes all the x coordinates negative of what they were. If b is less than 0. For our applications, we're going to be able to pretty much assume that b is positive. Okay, so we will usually assume that b is positive. The reason being that if b is negative, you can use the odd properties to make the minus go away or come outside and put it on a. So that's what's going to happen. Usually, we choose be positive. Because we can. And now we have the following result. Well, actually, let's leave that off for now. Let's see, here's the following result. This is what you do in algebra. I just want this as to bring some understanding to what we're doing, so you don't have to know this particular graph. If I have y equals x squared, I know particular points that this goes through. Right? If I put an x equals 1, y is x squared is 1. If I put an x equals 0, the square of 0 is 0. And if I put in minus 1, I get 1. All right? So those are 3 real common points that the y equals x squared curve goes through. What does the y equal 2x squared graph look like? You think of this as f of x is x squared. You think of this as 2 f of x. Right? So we're multiplying by number a equals 2. What does that do to the graph? It just doubles every y coordinate of this one, right? If y was 1, then now y will be 2 times 1 is 2. And so it looks like this. It looks twice as tall. At the point 1, now you've got y equals 2. At the point minus 1, you've now got y equals 2. But at 0, when you double 0, right? You still get 0. So what it does is it stretches at each point twice as far away from the x-axis. The ones above it stretches twice as high, the one below is twice as low. And now what if I plotted y equals minus 2x squared? What does it do to it? It just takes this one and flips it upside down, right? Because it takes the negative all these y coordinates. So now it goes down the same shape as this one, and it goes through the point minus 1, minus 2, and the point 1, minus 2. But 0, 0 stays where it is, right? So you flip over the y-axis upside down. But this is what you did in algebra. Maybe it looks familiar. Does that sort of look familiar or not? Okay. So now one of the big applications is the trigonometry. And then also you can think of this as y equals f of x, and this is y equals a f of x. Stretched by a factor of a is what it does. So this stretches by This is a stretch by absolute value of 2 and 2. And then this is a flip because you put a negative, a less than 0. Because this is a. So this one here is a stretch by whatever you multiplied it by. Absolute value of a is absolute value of -2 is 2, and a flip since a is negative. And now we can do the same thing with b. Suppose I start with, let's do this one. Y equals x cubed. Now let's just do y equals x squared again. Here's y equals x squared again. All right, and think of this as f of x. At those important points again. And what if I now, instead of multiplying by the function on the outside, I multiply the variable x on the inside and put y equals, replace x by 2x, right? So this is f of 2x, f of bx, b equals 2. So instead of multiplying the function outside by 2, I replace x inside by 2x. Then I get f of bx, and what happens here? Now, x only have to be half as big to square the same number, right? If x is a half, then I square 1. So I'll be at a half here and get 1. And instead of being a -1 to get 2, I'll have to be x equals minus a half, and then I square -1. So each number x will only be half as big. You get the same y value. And what that does is it squishes it in the x direction. You can also think of it as a vertical stretch, but for more general graphs, you want to think of it as a horizontal stretch. So this one, when I put b equals 2, the stretch factor in the x direction is actually 1 over b. Stretch by 1 over b equals 1/2. All right? And we won't worry so much about b being negative for our purposes, but you could get a horizontal flip if b is negative. We will usually select b less than b greater than 0, but if b is bigger than 0, there's a horizontal flip over the y-axis because it makes all the x coordinates negative. So I'll just mention that for general graphing strategies. We won't have to worry about that so much. Now we want to apply it to these two functions. Hence, and one more comment then. Then, if you take y equals a f of bx, put both an a and a b in there, what does that do? This does both a vertical and a horizontal stretch. So it has a vertical stretch by absolute value of a vertical flip if a is less than 0, and it has the b effect, a horizontal stretch or shrink if by 1 over b 1 over absolute value of b if b is negative. Let's just say 1 over b, assuming b is greater than 0. If b is less than 0, you also get a horizontal flip. Right. So this one is exactly that kind of thing. We take the sine and the cosine that we graphed, and we do the vertical stretch at absolute value of a, and the horizontal stretch 1 over b. And then we can do a vertical flip if a is negative. So suppose I want to sketch y equals minus, sorry, not minus, 2 cosine 1/3 x. Now I'm going to do on this one, let x be the angle instead of theta, right? I used theta equals the angle on the unit circle because I wanted to use x coordinates off the unit circle. But now that we're not doing the unit circle anymore, that was just to make the basic graph. I'll let x be the angle instead of theta. All right? Just to change the notation. That'll match the book and the homework for the graphs. How can I sketch that? What I can do is use my stretching and graphing techniques. I know what cosine looks like, right? Y equals cosine x. We memorize. It completes one wave as we go from 0 to 2 pi. And it goes between the guideline at y equals +1 and the guideline at y equals -1. And now these axes are x and y, like that. There's y equals cosine x. And it extends forever in both directions, right? Repeating. If that's y equals cosine x, how do I sketch y equals 2 cosine 1/3 x? I have to stretch it vertically by a factor of 2. All right. And then stretch horizontally by 1 over b. 1 over 1/3, which is 3. So it's actually going to be 3 times as wide and 2 times as tall when I go to sketch this one. And then there's no flip because these are both positive. So no flip. No vertical flip, since A is positive. All right, that would make all the y coordinates negative. And again, we'll choose B positive, so there's no horizontal flip. So, because B is positive. All right, so that's all I have to do to sketch this. How can I sketch the new graph? I make the graph now go twice as tall, so the maximum is going to be 2 and the minimum is going to be -2. And the guidelines will be here and here. All right. And now it used to go the whole cycle and get back up to the top in 2 pi units along the x-axis. Well, if I have a horizontal stretch by 3, then it's going to take 6 pi to get back where it started. So it's going to be 3 times as long because it's stretched out by a factor of 3. So it's going to start here. It's going to go all the way down to the bottom guideline and back up to the top. That's 6 pi instead of 2 pi. And that's how I can sketch it, right? I just to make it stretch by a factor of 3, I just make it finish a period after 6 pi instead of 2 pi, so it's 3 times as long. And I make the guidelines twice as far from the x-axis to take into account the vertical stretch too. And now what do these points cross? Well, here's what you notice about the graph also. This graph has a symmetry, right? It reaches the top points at 0 and 2 pi. The bottom point is exactly halfway in between, if you recall, pi, right? And what are these crossing points? They're halfway in between here and here. So it's got this nice pattern that every pi over 2 units, right? It starts at 0, it starts at 1, and then at pi over 2 units later, it's at 0. Pi over 2 units later, it's at -1. Then at pi over 2 units later, it's back at 0. Pi over 2 units at the top. So you can break this into 4 parts like that and sketch it. Similarly, this one then has to break into 4 parts. If this is 6 pi here, halfway in the middle, this has to be 3 pi because I just took this one and stretched it. It should still be halfway in the middle. And this one would be half of this one is 3 pi over 2. And this would be 3/4 of the way across, right? 9 pi over 2. So you can find all these nice crossing points. And now we think of something more general, because this algebra technique is pretty frustrating, and that you have to think of stretching it up and down, stretching it left and right, and then maybe you have to flip it. And it's hard to imagine that in your mind. What you do instead is you memorize these basic things I said here. Instead of trying to stretch every point and replot the whole graph by a table of points, you just take this graph here, and what you do is you draw new guidelines, absolute value of A times as tall, because that's the stretching factor, and you start at 0 and go to absolute value 1 over B times 2 pi to get the ending point. So what we did here, so the fast way to graph these, that if we incorporate these stretches, the stretches or shrinks. It's a stretch if the factor is bigger than one, shrink if the factor is less than one in absolute value. By calculating the amplitude of the wave is the distance from the middle to the guideline. Amplitude is always the absolute value of A, whether we had just cosine x, we said the amplitude is 1 because it's 1 unit from the center to the top. Now, when we double that, the amplitude is 2. We'll just say in general, the amplitude is absolute value of A. It's the stretching factor from 1 unit. And then the period, sometimes called P. Well, if the period was 2 pi and we stretched it by 3, we got 6 pi. In general, we take 2 pi times the stretching factor 1 over B. Assuming B is greater than 0, so we don't have a flip, then we need absolute value. So we just memorize these. Instead of saying it's stretched by this factor, it's a flip and so forth, we'll just say the amplitude between the guideline and the center is going to be absolute value of A. The period is always going to be 2 pi over B. And then we can draw these very quickly, right? And that'll do our stretches for us. We just draw the same wave in that fashion. So here's an example. Now I say, what is the sketch of y equals 1/2 sine of 5x? What does that look like, I wonder? It's an A sine bx, right? Whatever multiplies x is b, whatever multiplies the sine outside is a. And I can sketch it immediately by my graphing knowledge using the amplitude and period. What's the amplitude? Its absolute value of A, the absolute value of 1/2 is 1/2, right? So every point is going to be half as tall, and I can immediately draw the guidelines instead of a plus and minus 1 at plus and minus 1/2, right? So now it'll be half as tall if I just draw the guidelines here and here. Now, what about B? B affects the period, the distance it goes before repeating. So that's always 2 pi over B is 2 pi over 5. So what I have to do is I remember the sine function starts going through the origin, right? It has 0, 0. The cosine started at the top, the sine started in the middle at the origin. So I start here and I draw the same wave, but I just make it finish at 2 pi over 5. That takes into account the horizontal stretch, and go up and down between plus and minus 1/2. That takes into account the vertical stretch, and then I don't have to do all that crazy imagination. And then this will repeat over and over, so it'll go up and down and back again. Double this, 4 pi over 5, right? And so on. And it will go backwards the other direction and repeat at minus 2 pi over 5. And so on. Here's the sketch of y equals 1/2 sine 5x. How about that? Easy as can be, you just compute the amplitude and period, and it incorporates the vertical stretch and the horizontal stretch. And there can be a flip. That's the last example today. Suppose I want to sketch y equals -4 times the cosine of pi over 6x. I also want to illustrate something else. When you put a pi into b, here b is equal to pi over 6, this will make nice even units on the x-axis, right? Instead of getting pi at every multiple where it has a height, a maximum, or a crossing point here, when you put this in here, it'll be nice whole numbers. So let's see what we get here. This time a is a negative number, -4, and b has a pi in it, pi over 6. So what do I do for cosine? I remember that cosine starts at the top of its wave. And first what we do is we sketch the amplitude and the period. So the amplitude is -4. That says amplitude is absolute value of A, is absolute value of -4 is +4. Amplitude is always positive, right? Because it's an absolute value. Period, that's the stretching factor. That's what you want, right? Period is P is always 2 pi over B. Let me put it up here. Period is 2 pi over b, 2 pi over pi over 6. And be careful on these because people will say, oh, that's 1/3, right? It's not 1/3. What you do is you consider this to be 2 pi over 1 over pi over 6, right? Write them both as quotients, then it's top times bottom over middle times middle. So it's 2 pi times 6 over pi times 1, and now the pi's cancel and you get 12. They reinforce each other. So it's not 1/3 here. Multiply out carefully as quotient of quotients. And you actually have period of 12 units, but look, it's a whole number because I had a pi in here. And so what I'm going to get is I'll draw the period 12. That's where I want to finish one cycle of the wave. And then the amplitude of 4, I want the guidelines to go between plus and minus 4. And I can sketch this as quickly as can be without looking like the one man band trying to stretch and shift in my mind and flip. And then there's also a flip. So there's a period, an amplitude, and this one has a flip, yes, because A is negative. A equals -4 is less than 0. So now the cosine, remember, it used to start at the top, and this is what we used to get for the cosine. It used to go from the top guide, draw the guideline, given amplitude. Used to start at the top, but since I flipped it, the cosine is going to start at the bottom. So what I'm going to do is, at x equals 0, I'm going to start at the bottom guideline because it's flipped. And I'm going to draw the wave to the middle, up to the top, and back down to the bottom, like that. All right. So the cosine, the sine will start at the origin and go up and down. The cosine will start at the top and go up and down. The flip, and then you flip them upside down. The sine will start down like that, or the cosine will start at the bottom instead of the top. So here's a flipped cosine starting at the bottom. And what you do, all you have to do is draw the cosine upside down starting at the bottom. Right at the end of the period here was 12, right? And then it goes between the guidelines, -4 and +4. And that's it. That takes into account the stretch in both directions. And then what are these important points? Where is it equal to 4? It's like -4, doesn't it?
6.
Yeah, exactly halfway in between. So halfway in between 0 and 12. And here where it crosses is 3. Here where it crosses is 9. And you've got a nice graph as quick as that. All right. So that finishes here. We got about 1 minute left. I think it's time to put up the homework problems. Easy homework this time. 6.1, this is the new chapter. This won't be in the exam, but still I'm going to continue this discussion next time and finish 6.1. So I want you to look at these and try problem number 1. It's got several parts, so it's not like so trivial, but it's just graphing these kind of things. And that will help you to understand what we do next time, because next time we're going to move these around. We'll translate them, we call. Just stretch them. Next time we'll move them and figure out. And that's all engineers do with these things, is stretch and move them. And they're all called sine waves still, but now you've got waves that can oscillate real fast, right? Because we've stretched them in the y direction. We have different frequency sounds. You can have loud sounds modeled by this, by stretching them this way. And this is all they need, really. So do this, and also do the practice set that I'll put up on chapter 5 this weekend. All right? That'll be your homework for next time. And on Thursday next week, we'll review it. So thank you so much for coming in. Hope you have a nice weekend.